Good afternoon, and welcome to this workshop on ArcGIS Velocity, applying real-time and big data analytics. I'm Ken Gorton, and with me is my colleague, Peter Nasuti. We are product engineers on the real-time and big data team. During this session, I'll start off by illustrating how you can configure ArcGIS Velocity to process incoming feeds of data in real time to generate alerts and interact with external APIs. Then Peter will take over and illuminate analyzing huge volumes of data in big data analytics to look for events and patterns of interest. ArcGIS Velocity is a new capability that extends Esri's geospatial cloud, ArcGIS Online, with real-time and big data functionality. It provides a wide variety of capabilities for ingesting and working with observation and sensor data. You can just configure out-of-the-box connectors to bring in data from IoT platforms and third-party APIs. It's also an end-to-end system for analysis, supporting analyzing data in real time, in near real time with scheduling, and over time. And you can take immediate action as a result of your analysis, sending notifications or triggering downstream processes. The ingestion and processing of data through feeds, data sources, and analytics are configured with the Velocity web app. ArcGIS Velocity is very much an engine. It is a cloud system that runs real-time and big data jobs, which might be driving data to a layer in an ArcGIS dashboard, sending specific alerts, or collecting data over time for deeper analysis later on. And the new item types, feeds, real-time analytics, and big data analytics essentially map back to those three IoT challenges of ingestion, alerting, and analysis. Now, for this workshop, we're focusing on the analytic capabilities of Velocity. Peter will go over big data analytics in detail, while I will cover real-time analysis and alerting. And since all real-time analytics leverage feeds as data input, I'll also illustrate a little bit about ingesting real-time data. Oil companies have extensive operations that need to be monitored, including things like AIS vessel tracking, employee tracking, worksite analysis, and monitoring their helicopter fleet as they move workers and inspectors back and forth between the airport and offshore oil and gas fields, like the ones here in the North Sea. These moving tracks represent the real-time positions of the helicopters, and we're simulating the data at a much higher speed than they move in real life. This real-time visualization can be created through configuring a feed in ArcGIS Velocity. A feed is both a hosted data ingestion service and a live layer. Real-time data can be leveraged from existing ArcGIS layers, but more importantly, from cloud providers like Azure and Amazon Web Services, or from commonly used web and messaging systems and protocols. These include messaging brokers like Kafka, RabbitMQ, and MQTT. I can also configure a feed to receive data from external APIs, which can send data via post request directly to Velocity on a REST endpoint that I set up. Now, setting up a feed is very much a guided workflow that leads you through each step. In this case, there's an external system that can provide data in a particular schema and format. Here's an example of that schema. Velocity then gives me the opportunity to adjust certain aspects of the data model on the fly, such as adjusting field names, changing the field type, and even dropping fields that I don't need. I then identify key properties of the incoming data, such as how is location represented and how is time represented within the data, including data format and the field containing the time. And finally, where is the track ID located? The resulting feed has an item details page that explain things like the format details and geometry, as well as the schema of this feed. But more importantly, it provides the REST endpoint URL that external systems can send post requests messages to. And once published, data is continuously ingested and exposed via stream layer, which means new information is published to the map immediately. This means you can see changes more quickly, and you don't have to apply a refresh interval that taxes a data store with constant queries. So feeds are the first step in leveraging real-time sensor data, receiving streaming sensor data, parsing it on the fly, and making it available for visualization. Feeds provide you with an alternative to engineering and system integration. They're configurable and provide out-of-the-box support for a variety of common industry messaging technologies. The number of supported connectors will continue to grow over time. Feeds can be described as both system integration and situational awareness, but can be configured in minutes and without writing any code. Now, on to real-time analytics. Now, bringing in your data with feeds is just the first step. With real-time analysis, you can do more than visualize your sensor data. You can immediately put it to use. In Velocity, a feed is the input to a real-time analytic, which can be used to transform, enrich, and detect incidents. Real-time analytics are a flexible model building capability that let you combine tools and take different kinds of actions. You can store sensor observations over time in a feature layer, send notifications and alerts, or even send commands and triggers to external systems to actuate behavior. In terms of connecting to sensor data, Velocity includes out-of-the-box support for different real-time and big data systems. So for example, if you are leveraging IoT technology from Azure or Amazon Web Services, Velocity can grab data from those respective IoT gateways and enable it for geospatial analysis. If the data of interest is from a particular data provider's API, we have general HTTP feed types that can be configured to either poll the API at a regular interval or receive post requests from external APIs. And this includes support for user-defined headers, URL parameters, and post bodies. Now, if you have existing streaming systems, often they're using message brokers like Kafka, MQTT, or RabbitMQ. And Velocity can connect to those data sources securely. So these feeds, data sources, and output connectors are aimed at covering major commercial platforms, as well as common messaging technologies. This year, we're looking to add support for some of the most common AVL providers as well, like Verizon and Geotab, as well as Google IoT and BigQuery. Velocity also supports the most common data formats, delimited text, various flavors of JSON, XML, and so on. In the first demo, you saw how feeds support real-time visualization, but they actually go way beyond that as your doorway to real-time analysis and alerting. Among oil companies' interests in monitoring their helicopters is having a better understanding of how far they are from their destinations, whether that destination is an offshore oil platform or maybe the home airport on the mainland. Now, to do this, a real-time analytic can be configured to operate on every incoming observation or helicopter position. This analytic goes through three main steps, and I'll walk you through each one of these in turn. Now, this first step is to receive the incoming feed of helicopter positions and then calculate the motion statistics. And essentially what this does is look at a history depth of a number of previous observations and use that information to be able to calculate additional statistics about the movement of each helicopter. And these statistics include things like the heading, the speed, the total distance covered, the min, max, and average of these various statistics. It then performs a spatial enrichment operation to calculate the updated distance to each current destination, and it does so by comparing the current location of the aircraft to its destination. Now, one of the attributes that each aircraft includes is its destination. And here I brought in an additional data source of helicopter destination. You'll notice, first of all, that this is not a feed. This is a static data source. And every time this analytic runs, every time it starts up, it brings in all of the records from that static data source. In this case, it's coming from a feature layer, but it could also be drawn from an S3 bucket or an Azure blob or other static data source. But the calculate distance tool then essentially looks for the destination of the aircraft and tries to find a matching destination ID in this join data set. And it searches within a radius of 300 miles of that aircraft. And when it finds that destination, it calculates the Euclidean distance, the straight line distance from the aircraft to that destination, and then appends some additional information from that platform or the airport to the aircraft. And then the final step here is simply to clean up the helicopter observation information a little bit. Because these previous two steps, we've appended a lot of information to the schema of this observation. And we certainly don't need all of that for purposes of monitoring the position of these helicopters and estimating the estimated time of arrival, the ETA. So in our map field step here, essentially we've pared a lot of those fields down by simply removing them from the schema. But then we've also taken an additional step of configuring a couple of additional fields here. One is a float field where we calculate the time to destination, the number of minutes. And we do that by means of a simple arcade expression where we take the distance the distance to feature, which is calculated by that distance to feature tool in the previous step, and divided by the airspeed. Now the second field that we add here is a string field, and this is simply a message that indicates the estimated time of arrival in an easy-to-read text string. And to do this, we've used an arcade expression that is a little bit more involved than that simple expression in the previous field example. Here we've defined a function that we call ETA, and we pass in the current time plus the estimated time of arrival that we used by adding the time, the number of minutes calculated in the previous step to the current time of the helicopter. And then we specify that we want our result in hours, minutes, and seconds. It's basically the result of this is a text message or a text string that says estimated arrival in X number of hours, extra number of minutes, extra number of seconds. And then we output all of that information to a stream layer, which we can visualize on the map. So if we go back to our map here, I'll turn off the original feed and turn on that output stream from our analytic. And if I click on any one of these here, we see that that nicely configured pop-up here that tells the destination and indicates the current speed and the distance to destination, but it also indicates the estimated arrival in 20 minutes 31 seconds from the point where I clicked on that aircraft. Now, what if we wanted to send additional alerting based on when that aircraft is within 5 minutes or so or less from their destination? Well, one option would be to send a text message or an email output, and we can certainly do that. Email and output text messages are certainly part of our output options. But a more modern approach might be to send a message to an external system, such as the platform's landing pad, to turn on landing lights or other flight controls, or to send an automated pre-recorded message over a loudspeaker system alerting all personnel on the platform that an aircraft is inbound and arrival is imminent. So we can certainly put that in there, but we don't necessarily want to send such an alert for every single observation of the helicopter's position. So we want to precede that with an expression that filters all the messages to only send messages if the aircraft is within 5 minutes of the destination. And to do so is simply choose that minutes to time to destination _ minutes field. As long as it's less than, say, 5 minutes, then we will send that actuation message.
So here I have an external system that I've written. This is an extremely simple HTTP trigger function that running in Azure right now. So it's running in the cloud, and it provides a URL to which I can send messages. And this particular URL is, it's just a simple post request. And so the URL for that downstream client then is what I would place here in the URL, and I can then configure an outgoing expression to include in the post body. And I've already configured that here, so I'll copy and paste that from my notepad. And this basically is just going to send a JSON string of this dictionary, indicating the aircraft, the destination, the number of miles remaining until that aircraft arrives, and then the estimated number of minutes, plus that outgoing message that we configured, estimated arrival in X hours, minutes, and seconds. And you see that this compiles a dictionary for me. The message here indicates, of course, that while this expression evaluates a dictionary, we need to have a JSON string, so use a text function. So I'll go back in here, and I'll simply add that text function in before the dictionary. And there we have a nice JSON string configured. So I'll save this analytic, and that'll cause it to restart and reinitialize. So now that it's started, we can go back over here to my output utility, and we'll take a look at the log here, where it should be logging those messages as they come in. So here we can see that my velocity analytic is sending those messages right along. We have here, for example, here's an aircraft inbound to Aberdeen Airport, estimated arrival in 2 minutes, 21 seconds. You can see that those messages continue to come in.
In GIS, we're all aware of the power of spatial analytics to understand patterns in data over time and make better decisions for our organization strategically. Real-time analytics are useful when your decision timeline is operational, when you want to know about something and take action right away. Real-time analytics provide processing horsepower to your tracking and sensor workflows. Again, they enable you to set up automated, spatially aware processes without having to build a custom streaming application or maintain hosted Python or other scripting code. As you saw, real-time analytics process each message from a feed continuously as it arrives. But they can leverage static data sources as well to serve as geofences or enrichment data. So in the oil company's helicopter tracking use case, I merged the various drilling platforms and the airport into a single feature layer, and the distance from destination calculation is done against that data. Supporting data sources like this can come from feature layers, but also straight from cloud sources like Amazon Web Services S3 buckets or Azure Blob stores. The configurable nature of these analytics is a lot like Model Builder in our desktop clients. You combine different tools together in a workflow, and you can ask several questions at the same time, associating different output behaviors in each case. For example, in the same real-time model, you might have branching processes where one branch performs a geofencing operation that sends a particular alert, but you might configure another branching path to include an output feature layer to store all of the data, and yet a third process path that stores only the latest observation of each track. This is a useful pattern when you want to enable visualization of the latest observation, while also maintaining a log of historical data for future analysis of patterns and trends. The first supports downstream apps and clients such as dashboards to pull for fresh data and always have the latest updates. But also storing all of the data over time enables things like the display of breadcrumb trails of moving assets, and more importantly, future analysis of the accumulated data. Now, this can often be a challenge because as data arrives in real time, historical data sets can very quickly grow to huge volumes of millions of records, and it's hard to work with or visualize those kinds of feature volumes in an exploratory manner. For these cases, ArcGIS Velocity also includes fully configurable analysis tools so that you can process this information for patterns and trends. So now I'll turn it over to Peter, who will walk us through big data analytics.
Thanks, Ken. For the rest of this presentation, we will switch our focus to big data analytics within ArcGIS Velocity. Let's quickly review the core concepts of what big data analytics are and what they offer before diving into specific demos and more advanced concepts. Big data analytics allow you to apply spatiotemporal processing on your data, even if it's large in volume, in a hosted configurable service. These analytics are capable of processing anywhere from hundreds of records to billions of records. With a big data analytic, you bring stored data into the analytic as opposed to data in motion. This is achieved using sources. This source data often comes from ArcGIS feature layers, yet various additional source types are available, including cloud stores like Amazon S3, Azure Blob Store, and Azure Cosmos DB, and other source types including HTTP Polar and RSS Polar. Once data has been configured to enter an analytic using data source configuration, analysis can be performed. Tools can be chained together to form a larger analytic process without having to maintain a custom script or build a custom application. Once your analysis is planned, one or multiple outputs can be configured in the analytic to dictate where results and data from your analysis can be sent or stored. Any source or tool node can send the features from that step in the analytic process to an output. Consider if you're performing an in-depth pattern analysis exercise, you would perhaps want to push the results to an ArcGIS feature layer to explore in a web or desktop client application. In other use cases such as incident detection, the main purpose might be to drive outputs such as email or text message alerting. When first planning and configuring big data analytics, it's important to consider the following three elements to integrate successfully with your operational environment. What source types will I use to load my data? Does the data live in an ArcGIS feature layer? Maybe my data is in an Amazon S3 bucket or Azure Blob Store in the cloud. Or perhaps I'm collecting data from a vendor's web API using the HTTP Polar source type. Then we want to ask, what output type or types will I use? Where do we want to send the results of our analysis? Output features can simply be added to an ArcGIS feature or stream layer for use in the ArcGIS platform. Alternatively, analytics can be configured to send email or text message alerts when certain criteria are met. These big data analytics also support writing data to other outputs such as Amazon S3 stores, Azure Blob Stores, Azure Event Hubs, HTTP endpoints, Kafka, and more. And finally, we want to consider what format is my data being ingested in and what format is my data being exported in. When you're configuring your data in sources, ArcGIS Velocity will automatically sample and help you determine and configure the data format and specifications. When configuring outputs, some outputs require you to choose the desired output of your format, such as a certain flavor of JSON, delimited, shapefiles, and more. Once a source has been configured, it's time to configure analysis using the available tools. ArcGIS Velocity groups tools into various categories, including analyzing patterns, enriching data, finding locations, managing your data, summarizing data, and using proximity. You'll also notice that big data analytics have more tools available than real-time analytics. This is because there are additional types of analysis that can be performed on a collected set of data when compared to processing just individual features. All these tools can be utilized in concert together to design an analytical model that processes your data sources and enables users to answer complex questions. Let's look at these components and capabilities in action. For our first big data analytic demo, consider the California Department of Toxic Substances Control, or DTSC for short. This government entity holds the ongoing mission of protecting California's people and environment from the harmful effects of toxic substances. The DTSC is responsible for recording and understanding the transportation of toxic materials from producer facilities to destination facilities. As these materials are in transit, there could be potential for risk to the regions that they drive through in the event of an accident or spill. Therefore, let's address the following question in our demo. What schools and hospitals in California are at the greatest risk from the transport of toxic substances? To answer this larger question, we must first understand, where do the trucks go near schools and hospitals? And for locations identified where trucks go near schools or hospitals, what is the total cumulative time that trucks have spent within a given distance of a school or hospital? This will bring us to our demo. Let's go ahead and start building this analytic. First, we will click Create Big Data Analytic on the Big Data page. The first data set we are loading is the truck vehicle track points, GPS track points of the toxic materials in motion. This data would be acquired via feed in a real-time analytic and then stored in an ArcGIS feature layer. The data being loaded from this is DTSC track points for 1 week in July 2019. And it holds a week of truck movement between these actual origins and destinations, however, with simulated routes. We'll click Next to proceed. We will change our output spatial reference to 102, the Web Mercator Web Auxiliary Sphere, projected spatial reference, which will support our later use of a near planar spatial operation. All fields and schema are satisfactory, so we'll leave them configured as they are. We will not set a timestamp field as we are processing all features in this feature layer for a single ad hoc analytic run. Key fields are already identified, representing the start time of each record held in the timestamp field, and the track ID, which in this case is the route manifest ID. Let's click Complete to finish this source setup. This brings us to the analytic configuration environment. Let's click to Create Analytic and provide a title and description, which also saves our analytic. Our title will be Calculate DTSC Risk to School and Hospitals, and we'll provide a description to explain this model. Once saved, let's switch to the model view of ArcGIS Velocity to support our configuration of a more complex analytic flow. Next, we need to configure another data source to load in the school and hospital point features. We will click Sources, Feature Layer to configure this additional source. The name of this layer is Sensitive Receptors City, and we will select this layer and click Next to proceed. For this layer, we will also designate an output spatial reference of 102.100 and leave all other settings default and finish this configuration. We can rename nodes in the model for clarity. For example, let's rename sensitive receptors to show that this node ingests data representing schools and hospitals. Now that we have our truck observation track points and our schools and hospitals, we're ready to answer the first question of where do trucks go near schools and hospitals? We will first add, connect, and configure the Detect Incidents tool. This tool creates incidents from the observation track points whenever a user-defined condition is met. In this case, we will set a spatial incident condition where the truck is within 100 meters of a school or hospital. Let's look at what the output of this tool would look like if run. This 100-meter buffer shows us the distance of concern from the specific school facility. As you can see, a truck was driving south in this area. It satisfied our condition, being within 100 meters of the school, so the Detect Incidents tool identified the situation and created an incident. The first observation track point within the distance was identified with an incident status of started. Subsequent observations were ongoing. Once the truck was no longer within the given distance, the incident completes and the next observation outside this condition has the status of ended. Notice that for the ending feature, the Detect Incidents tool has generated a field called Incident Duration, which represents the duration of the incident in milliseconds. We will use this value in later processing to understand the summary time of toxic waste proximity across all incidents. Now that we have detected incidents, let's filter out these features to retain only the ending features. We are only interested in the final duration of each identified incident. To do this, we'll add and configure a filter by expression tool in our model. We will connect it to the output of the Detect Incidents tool and use the Arcade Expression Builder to configure an expression of features incident status is equal to ended. We'll test this, click OK, and click Apply. Next, we will configure the Calculate Distance tool to calculate the distance between each incident ending feature and the nearest school or hospital. This tool will search for the nearest feature within a 250-meter radius. Furthermore, this tool enables us to enrich each ending incident feature with the attributes of the associated school or hospital. This is necessary to support later summary processing. Reviewing the schema that will come out of this Calculate Distance tool, the output will append the following fields: location name, location type, location name with ID from the join schema, as well as the calculated distance to feature. These are necessary for summary processing. Our next step is to configure a Join Features tool. This tool will take schools and hospitals as the target dataset. We will specify the outcome of the Calculate Distance tool as our join dataset. This tool will perform a one-to-one attribute join where we retain all features. The attribute join will be between the unique location name with ID field, which resides in both datasets. We will then configure a summary field on the incident duration field to perform a sum statistic operation. This tool will start with schools and hospitals, and then for each school or hospital, we'll summarize all detected ending incident features that join to that school or hospital and report the sum of time that any and all vehicles carrying toxic substances had been within 100 meters of this facility. Finally, let's configure a feature layer output to store the results of this analysis. We will add all new features, and each time the analytic runs, we will replace the output. We will name this output feature layer Schools and Hospitals Toxic Substance Proximity Summary, complete, and connected to the model. We'll click our Auto Layout button and choose our best fit to view the complete analytic. At this point, I would save the analytic and start it to perform analysis and generate my output features. For the sake of time, an identical analytic has already been run and generated output, which we can now review. In this web application, we're looking at this output feature layer and are symbolizing the incident duration sum of each school or hospital feature. This enables us to quickly visualize and identify which schools and hospitals are close to busy roads for toxic material transportation. With this output and in this application, we have answered our original question of what schools and hospitals in California are at the greatest risk from the transport of toxic substances. This kind of intelligence is integral to the mission of DTSC to ensure that vulnerable community resources are kept safe. Findings from this analysis could be used to plan and promote alternate and safer routes for transport companies, or to coordinate with transporters if their drivers tend to make stops in sensitive areas. We have now demonstrated how ArcGIS Velocity offers a solution to model and execute an analytic process with multiple steps and run it as a cloud service to process tens of millions of features. For many organizations, this is a welcome alternative to on-premises desktop processing workflows. This will conclude our first Big Data Analytics demo. The scenario we just worked through was an example of an ad hoc analytic. This means that when the user clicks to start the analytic, it runs once and stops running when processing and analysis is complete. However, Big Data Analytics and ArcGIS Velocity have another powerful capability. These Big Data Analytics can be configured to run at a defined frequency or on a schedule. Big Data Analytics can be scheduled to run as often as it takes to complete the processing, with 1 minute being the fastest cadence allowed. Overall, Big Data Analytics are useful certainly when your decision timelines are strategic, when you need to learn over time and adjust larger approaches. However, with scheduling, they can also be tactical when you need to respond or be aware of information in near real time. As Ken had already covered, feeds and real-time analytics work together to ingest, process, analyze, and store observations in real time as features are received by ArcGIS Velocity. In addition to this, recurring big data analytics can be configured to use the output of the real-time analytic as its data source. Using such a feature layer source and configuring the timestamp field parameter, we can configure an analytic to load in only the most recent features processed by the upstream real-time analytic and process these new features in batch analysis each run. This enables users to create scheduled analytics which run frequently that process batches of recent feature observations in near real time. Such analysis enables summary and pattern analysis that could not be detected at the real-time analytic level. Let's show this concept firsthand with another demo. We will look at 311 reports of parking issues or violations in the San Francisco region. I have already configured a feed to ingest the most recent 311 features. For the purpose of this demonstration, this is an HTTP simulator feed that consistently ingests 311 features representing issue reports from the San Francisco region. Additionally, there is already a real-time analytic configured. This analytic connects to the 311 feed and writes the data to a feature layer that keeps the latest updated version of each reported 311 incident. If we look at the feature layer output of this real-time analytic in a map, you can see that there are a variety of report types available from the 311 data, such as parking incidents, public works, waste services, transportation, and more. For this analysis, we will configure a new big data analytic that creates a near real-time informational product presenting hotspots of just parking issues for the San Francisco region every 30 minutes. Let's click to create a new big data analytic, and we will configure a feature layer source pointing to the output of our existing real-time analytic. We recall that the name of this layer was San Francisco 311 events keep latest, so we will select that feature layer. For the filter data step of this feature layer configuration, we will configure a where clause to only return our parking issues. The expression we'll use is category equals parking enforcement, and we will also set a spatial reference of 10 to 100 to load the data in a projected spatial reference. We'll proceed and leave the existing schema configuration. This brings us to the timestamp field parameter. A timestamp field can optionally be configured. The timestamp field parameter is a date field specified by the user, which is utilized to only load new features that were added to the feature layer since the last recurring big data analytic run. In this case, our timestamp field is a field called opened. For example, if a big data analytic runs every 30 minutes, each time it runs, it loads data from the feature layer with an opened date value within the past 30 minutes. We will complete our source configuration with start time and track ID already identified, and this will bring us to the big data analytic. Next, we will configure the Find Hotspots tool. This tool will identify any statistically significant hot and cold spots in the spatial pattern of our data. In this tool, we will configure half-mile bins without time stepping. The output of this tool will be half-mile square bins representing hot or cold spots in the data. Next, we'll add a Calculate Field tool and configure a new date field called Date Time Processed. For this field, we will configure an arcade expression using the Now function to append the time of feature processing. This will enable us to use a time slider to review recent and historical hotspot results for parking issue reports in this region over time. Next, let's configure a feature layer output to hold the results of our hotspot analysis. For this output, we will choose to always add new features as there's no track ID for these generated hotspot polygons. Additionally, each time the analytic runs, we will keep existing features in schema. This means that the output feature layer always has the latest analysis results as well as the archived results over time. We can assign an output layer name of San Francisco Region 311 Parking Issue Hotspots and click Complete. Next, let's create the analytic and give it a name. We'll call this analytic San Francisco Analyze 311 Events. And optionally, a summary could be provided below. Once the analytic is created, we can configure scheduling by clicking the Schedule button on the upper right. We will set this analytic to run periodically every 30 minutes on every day. And click Apply, and then we'll save our changes. Once all this is configured, the analytic can be saved and started. This analytic is scheduled to run every 30 minutes from midnight. So if we were to start our analytic at 8:55 a.m., it would run at 9 a.m., 9:30 a.m., 10 a.m., and so forth. There's already an identical copy of this analytic running, which I have switched to here. Looking at the logs, we can see that this analytic has already been running on a schedule for some time now. We can look at the output of that analytic, which already has relevant symbology applied and collected features over time. As you can see, time animation is enabled on our date time processing field that we calculated. This allows us to visualize the hotspot results for each prior 30-minute run result of the analytic in near real time, as well as the latest results. This can help city managers identify unknown or unplanned for events, provide additional transportation or police support, and ensure city resources are being allocated effectively. As we have seen, when big data analytics are scheduled, they offer a powerful new capability to perform near real-time analysis and generate up-to-date results and informational products to support your organizational workflows and needs. With that, we will go ahead and conclude our presentations and demos and open the floor for a question and answer period.
All right, thanks so much for joining us today to learn more about the real-time and big data analytic capabilities of ArcGIS Velocity. So I'm joined with Peter Nasuti and Ken Gordon here. My name is Greg Team, and I'll be moderating the Q&A. So let's go ahead and kick things off with the first question. So we're going to go through these questions based upon the number of thumbs up you guys gave. So the first one is, what are the differences between ArcGIS Velocity and GeoEvent Server? Peter, do you want to take that one?
Sure, I'll take that one. Thanks, Greg. So there's some key differences between ArcGIS Velocity and ArcGIS GeoEvent Server and GeoAnalytics Server, which some of you may already be familiar with and have worked with in the past. Key differences center around the product's capabilities and the inherent business model. At its main component, GeoEvent Server and GeoAnalytics Server are on-premises software. For example, you get a license to the software and you install the software on your own server machines on premises or in the cloud, whereas ArcGIS Velocity is software as a service. Similar to how ArcGIS Online, it's available to you, you access it through a browser, and you configure it to do the things that you need. Some key differences and capabilities available in ArcGIS Velocity are that Velocity has built-in high availability and disaster recovery. Velocity is deployed automatically, so after acquiring Velocity, you'd wait 30 to 60 minutes to get access to the application. When you're storing data in Velocity, it's stored in the cloud. And keep in mind, this is software as a service, so it's not directly extensible as far as writing custom code and components, but as Ken will talk about later, there's quite a few other ways to integrate with your systems. And this is offered really as a subscription. Now, not only does ArcGIS Velocity offer a lot of similar capabilities as well as other capabilities to GeoEvent, but you can also perform big data analysis and create a pipeline of tools and chain that analysis together to create some really complex analysis and answer quite a few different questions with the tools available.
Great, thanks, Peter. Ken, one for you. Can you perform geofencing between two different real-time data streams?
Sure, yeah. Geofencing between two different real-time streams is something that we're currently working toward for the next release. We refer to that as dynamic geofencing. Currently, we can do geofencing between a live stream against a static data set, a data source. But the challenges involved with essentially, geofencing two live data streams are currently being developed and toward our next release in June. Now, that being said, you can approach geofencing to almost live, near real-time streams if you use a recurring big data analytic. And so you'd every time that analytic would run, then of course you'd ingest 2 different data sources. And if those the data has changed since the last time the analytic ran, it will work on, it'll do the geofencing on the latest version of the features and the data. So dynamic geofencing in real time coming with our next release, and then near real time geofencing of 2 different changing data sets. You could do it a big data analytic that's scheduled.
Perfect. Thanks, Ken. Next question, Peter, how does licensing velocity work?
Sure. Thanks, Greg. So that question, we'll kind of take a step back to remember that ArcGIS Velocity is inherently a subscription to software as a service. So if your organization wanted to move forward and implement ArcGIS Velocity, you would work with your Esri account rep and choose what subscription license you feel like best meets your need. So we call these 3 different licenses: standard, advanced, and dedicated. And each successive license level adds additional functionality and processing speed to the previous level. Now, in our demo and our presentation today, we showed creating feeds and using feeds, publishing and running real-time analytics, and also looking at big data analytics. And you can do all 3 things: feeds, real-time analytics, and big data analytics at any license level: standard, advanced, or dedicated. As you move up to the higher license levels, such as advanced, you can also publish and run scheduled big data analytics, which you saw in the final demo just recently here. And then in the dedicated license level, you also have the ability to scale big data analytics for faster run times. So for example, if you wanted to start processing tens or hundreds of millions of features or billions of features, you'd want to provide some additional resource allocation to those big data analytics so that they complete in a faster time to meet your workflows. So there are additional options there as the license levels increase. There are limits on processing and storage capabilities based on the license levels. For example, ingestion velocity is measured overall in kilobytes per second on average. So for standard, you'd have up to 25 kilobytes a second, advanced 250, and dedicated 2,500 kilobytes a second or higher. Storage capacity is the same way. How much storage you have available to hold your ArcGIS velocity level increases at the different levels. In your standard and advanced license levels, you have a cap on how many running feeds and analytics you can have, which increases by license level. And in dedicated, you can really run as many fit available to your compute and storage. Now, there's additional flexibility built into these license levels. For example, if your organization started with standard, but then realized that they need more capability and compute power and running items, that could be increased to an advanced or dedicated license level. And when you're in an advanced or dedicated license level, you can add additional item, compute, and storage units to support additional use cases and workflows. So overall, the takeaway is that there's 3 different license levels with some additional flexibility built in to try and meet whatever your organizational needs are.
Perfect. And to expand upon that one a little bit, Peter, the next one is, how are users managed with Velocity? Do users need to be individually licensed?
Sure. I can go ahead and expand on that. So with ArcGIS Velocity, your organization would purchase a subscription to ArcGIS Velocity, and that's the cost. There's no per user allowance of what you can or how many people you can add. Once you have ArcGIS Velocity and you want to give access to the people within your ArcGIS Line organization, you can create a custom role for Velocity and control whether users can create feeds, create real-time analytics, or create big data analytics as custom role content options. So you have an additional granular control over what the people in your organization are allowed to do. As soon as a user has any one of those 3 options, they'll see the ability to jump into ArcGIS Velocity, and they could get started creating items, whether it's feeds or analytics, and then working with the output of that.
Perfect. Thank you. Next question. Are there any new tools in the upcoming release of Velocity? Ken, do you want to try that one?
Sure. Yeah, so in our we have 3 new tools coming out in the next release of Velocity, and there are 2 in the real-time analytics, in particular, event volume controller, which throttles the number of outgoing events from a given analytic, and detect gaps, which basically it watches an incoming stream of data, and for each of the tracked assets, objects, entities, if the incoming stream is interrupted for that particular track, then for a certain amount of time, that is considered to be a gap, and then it issues
it sends out an alert, a notification that there's a gap has been detected. And then in big data analytics, we have generalized linear regression, which is a new tool that will be included in the next release as well. So I encourage you to stay tuned for those as well.
Perfect. Thanks, Ken. Peter, next question. What storage service does ArcGIS Velocity use? What's the storage capacity for ArcGIS Velocity?
Sure. So with ArcGIS Velocity, being a software as a service hosted in the cloud, your data is residing in a cloud in a data store with elements of the big data store and spatiotemporal nature of storing your data and enabling you to do things like dynamic aggregation and visualization of large numbers of features and so forth. The data amount that you can store, again, depends on your license level. So the standard license level by default has 100 gigabyte storage capacity. The advanced starts with 1 terabyte storage capacity, and the dedicated starts with a 3 terabyte storage capacity. In those advanced and dedicated license levels, the storage can be augmented by purchasing additional storage units. So if your organization was building up data faster than you'd expected and you wanted to keep all that data, that could be augmented by increasing the storage available to your subscription in your organization.
Perfect. Next one, will Velocity be available for enterprise users to be hosted on their own Azure AWS instance in the future? Peter, Ken, which one of you guys want to take that?
I can take it. Peter, feel free to chime in if there's something
Sure.
that I miss or you want to. Anyway, yeah. So that is something that a lot of people have asked about. They're interested in it. People in a number of different industries, and it's something that we do have in our sort of our roadmap for the future. We don't yet have a schedule or a timeline for when we intend to be able to roll that out. But it is something that we are very definitely working toward, we're excited to be able to be in the process of developing that as well.
Perfect. Peter, how do I get started and set up Velocity?
Sure. So being that it's software as a service, that process is really simple. You just contact your Esri account representative. You'd want to decide what license level is right for you. There's documentation on what the different license levels offer. Purchase ArcGIS Velocity, and in 30 to 60 minutes, you'd get a notification that, hey, ArcGIS Velocity is provisioned and it's ready for you to use and access. And then again, you would need to, for non-administrators, you need to create a custom role to grant a non-administrator access. But of course, an administrator would be able to access it as soon as provisioned, so right away.
Great. All right, Ken, how can I bring in data from real-time APIs that Velocity doesn't have out-of-the-box support for?
Yeah, it's the answer to that is really twofold in terms of real-time analytics, and one of those would be an HTTP poller. So if there's an external resource that exposes data on some sort of an HTTP endpoint, you can configure a real-time feed to ingest from that data, and or a data source in a real-time analytic or a big data analytic to periodically poll that data source for updates of information. Another way would be to set up an HTTP receiver, and that is more of a passive ingestion point where Velocity essentially sits and listens on a REST endpoint, and then external systems can in turn send data to that. And there is an example of that we included in that first demo that I did in the real-time analytics section of today's presentation.
Great, perfect, thanks.